Hey there! Today we're diving into the fundamentals of robotic motion. How do these machines actually move? Let's look. Think about a delicate surgery. How does a robot know exactly where to slice? Well, it's all about anatomy. Specifically, it's muscles. In robotics, we call these mechanical muscles actuators, and they totally control the machine's movement.
Let's compare the big three motor types you'll see: DC, stepper, and servo. Each one has a distinct job.
First, DC motors. Sure, they're cheap and powerful, but they completely lack accuracy and speed control. Not great for surgery. Then we have servo motors. These are super smart, offering ultra-smooth control and automatic correction, though rotation is limited. Finally, it's stepper motors. They turn electromagnets on and off to move in exact steps, perfect for precise, continuous control. By rapidly firing power to different magnets in sequence, the motor hits a perfectly controlled step angle every time. To put that into perspective, a 3.6-degree step angle means exactly 100 precise steps per single revolution. But here's the catch. How does the robot's brain actually know its muscle moved correctly? That's where a feedback control system comes in. It constantly adjusts inputs to hit a target output, no matter what. Kinda abstract, right? Let's use a super relatable example. Your car's cruise control. A controller takes your desired speed and constantly checks it against the actual feedback from the car's odometer. It literally calculates the error between your target speed and reality and then adjusts the pedals to match. This brilliant loop rejects physical disturbances like steep hills or wind, keeping your motion totally stable and optimized. So what happens when perfect motors meet perfect feedback loops? You get absolute game changers, like medical robotics. Just look at the Da Vinci and Oculus systems. These life-saving surgical and rehab robots are literally revolutionizing healthcare. They can handle complex 3D imaging, precision navigation, and tremor-free motion replication for those incredibly delicate surgeries. We're even seeing cutting-edge robotic exoskeletons controlled by brain-computer interfaces to help stroke patients walk again. So, if our brains are directly controlling the machine's loop, where does the human end and the robot begin?